Hello, my name is Noam Brown. This is joint work with Tomas Santom and Brandon Amos, and our paper is on depth-limited solving in imperfect information games. This paper focuses on imperfect information games, which are strategic interactions that involve hidden information. Some examples are negotiations, financial markets, elections, security interactions, and the classic benchmark for research in these games is poker. Now, the presence of hidden information means that algorithms used for other games like Go and chess don't work anymore. So new techniques are needed in order to handle hidden information. A major milestone in this line of research occurred in 2017 when our AI Libratus decisively defeated 4 of the world's best heads-up no-limit Texas Hold'em poker players in the world. The competition involved 120,000 hands of poker, and each human lost individually to the AI. But this victory wasn't cheap. Libratus needed 3 million core hours and about 25 terabytes of memory in order to beat these pros. And the algorithm it used doesn't easily apply to other games without a major increase in the expense. So this paper asks, can we make an AI that is nearly as good as Libratus, but much cheaper and more general? And it turns out that the answer is yes. Okay, so for starters, let's talk about why Libratus was so expensive. And the first thing to understand is that real-time planning is really important for any game, not just poker. In fact, it was essential for reaching a superhuman performance in Go and chess, and even backgammon as well. In chess, the real-time planning algorithm that was used was alpha-beta pruning search, and in Go it was Monte Carlo tree search. In poker, it was an algorithm called nested solving, which is discussed in our paper from last year that won Best Paper. In perfect information games, this real-time planning is easy. You take some action, your opponent takes some action, and now you're in what's called a subgame. And the remaining subgame might be too large to solve, but that's okay, because we can solve what's called a depth-limited subgame instead. Basically, the idea here is that you only search up to some depth limit, and then you reach what's called a leaf node at that depth limit. And at the leaf node, you substitute an estimate of the value of both players playing optimally from that point forward. And if those estimates are perfect, then doing this depth-limited planning, this depth-limited search, will in fact give you an optimal policy to play. The problem is that state values are not well defined in imperfect information games. And here's a simple example showing that. This is a simple game that I call Rock, Paper, Scissors Plus. It's shown on the left here. It's just like Rock, Paper, Scissors, but if either player chooses scissors, then the winner gets 2 points instead of 1. And that's simply to break the symmetry of the game. The game starts with player 1 choosing an action, but player 2 doesn't see what action they chose. And that's signified by the dotted lines between the 3 player 2 nodes. Then player 2 is going to choose an action, and then a reward is received. The reward here is shown only for player 1 because player 2 simply receives the opposite of whatever player 1 gets. It turns out that the optimal strategy in this game is to pick rock and paper with 40% probability and scissors with 20% probability. If both players do that, then they're in what's called a Nash equilibrium where neither player can improve, and player 1's expected value for each action is 0. Now I want you to imagine that you're player 1 in this game and you're trying to solve a depth-limited version of this game with a depth of 1. So traditionally that means substituting the value of the equilibrium of the state at the depth limit. But like I said, the equilibrium value of each action is 0. So if we try to solve a depth-limited subgame, then that would mean that each action leads to a leaf node of value 0. And that's shown on the right here. And it's really easy to see that if we were to try to solve this depth-limited subgame, there's no way we would arrive at the optimal policy of 40%, 40%, 20%. There's simply not enough information in this subgame to reach that policy. And the problem here is that we're assuming player 2 is playing a fixed strategy. That is, we're assuming that they are always choosing rock and paper with 40% probability and scissors with 20% probability, regardless of what our policy is. And indeed, if that were true, then it wouldn't really matter what strategy we play. We could pick rock 100% of the time, and we would actually get an expected value of 0. But the problem is that if we actually did that, then player 2 would adjust. If we were to always choose rock, then they would switch to always playing paper, and the value of the states would change. So this means that we have to consider how the opponent can adjust to counter our policy that we choose in the depth-limited subgame. And this isn't just a hypothetical issue. This is a real practical issue, and we show this in the paper. So what do? In Libratus, we just avoided this whole problem by simply solving to the end of the game. But that's expensive, especially if the game is really deep. So what we do in this paper instead is explicitly consider the different ways our opponent might adapt to our policy and try to find a policy that is robust to those adaptations. So at a super high level, because I'm trying to keep this short, what we do instead is, instead of simply assuming the opponent will play the estimated equilibrium policy after the leaf nodes, we give them a choice between a few different policies. Each of these policies result in a different set of values for the leaf nodes. We find this set of policies using an iterative process. First, we assume the opponent can only choose a single policy, which is just the equilibrium policy that we've estimated. In the case of rock, paper, scissors plus, that means we're assuming they always choose rock and paper with 40% probability and scissors with 20% probability. Then we solve this depth-limited subgame, where the opponent can only choose that policy at the leaf nodes. For example, that might mean that we arrive at picking each action with 1/3 probability. And now we calculate what policy the opponent could play to best counter the policy we've just computed. In this case, that would mean always picking rock. So now we add that policy to the set of policies the opponent can choose at the leaf node. And then we repeat this process. And now when the leaf node is reached, the opponent can choose between those two different policies. And this process repeats for as long as we want. And we find that even with less than a dozen opponent policies, we get very strong performance. In fact, using this approach, we were able to construct a poker AI we call Modicum that beats two prior top AIs. One was Baby Tartinian 8, which used 2 million core hours and 18 terabytes of memory. The other was Slumbot, which used 250,000 core hours and 2 terabytes of memory. Modicum beat both of them and only needed 700 core hours and 16 gigabytes of memory, and played a hand of poker in 20 seconds using only a 4-core CPU. So the key takeaways of this paper are that in imperfect information games, you have to consider how the opponent can adapt to your policy when you're doing real-time planning or search algorithms. And states don't have well-defined values. Our solution to this problem is sound, and it led to Modicum, which is the second strongest poker AI to ever exist, and was built using resources found in a typical laptop. Thank you, and please come by our poster session.